Hello, everyone. My name is Dominique van der Mensbroek. I'm with the Center for Global Trade Analysis at Purdue University. I'm really happy to be chairing this webinar on a new version of the GTAP database called the Circular Economy Database. It will provide many analysts with additional levers to be looking at scenarios of dematerialization, which is an important policy issue that many people are looking at across the world. I'll let Maxim go into the greater details. So let me introduce Maxim, who is a research assistant professor at the center. He's been with us since, I believe, 2017, and has been working a lot on climate change, on trade, on the circular economy, as well as doing a fair amount of country-specific work. Before Maxim gets started, just a word on protocol. Please have your mics muted during the entire session. If you would like to raise issues during the discussion, just write in the chat box, and then when we have the Q&A, you can raise your hand and be acknowledged that way. So without further ado, Maxim, the floor is yours.
Great, thank you, Dominique. Let me share my screen. Okay, can you see my screen well? Okay, great. Yeah, good morning, good afternoon, good evening, everyone. So as Dominic has already introduced, my name is Maxim Chepelev. I'm research assistant professor at the Center for Global Trade Analysis. And in this presentation, I will be discussing a database, GTAP Circular Economy database that we have recently developed. I will start with some introduction motivation for this work. Then I'll discuss our methodology, how the database has been developed, and provide a brief overview of the database. And then I'll discuss a couple of applications that this database has been used in, and in particular, we'll focus on one application that discusses the circular economy transition in Europe, work that we have done with the World Bank. And finally, I will close with some conclusions and some of the future developments, actually ongoing developments on further extending this work. Okay, so in terms of the motivation for this work, current material patterns are projected to put pretty substantial pressure on Earth's ecosystem. So if you look across studies, many project that with current population and economic growth trends, material use can increase substantially 2-3 times by 2050, depending on different studies and approaches. And of course, it puts substantial pressure both on number of environmental dimensions, ecosystem services, emissions, water, land pollution. So it's obviously a major environmental issue. And it's widely recognized that there is a need to move towards a more sustainable and consumption and production patterns, and the concept of circular economy has been introduced and widely used in this regard to reduce, with an aim essentially to reduce the material throughput, or reduce the consumption of material per unit of output or per unit of use. So in order to properly kind of represent this type of scenarios, policies related to circular economies, specific features need to be present both in the database and in the model. So first, country-specific production volumes across different technologies need to be properly represented in their database. So think of how much steel is produced using primary technology or using secondary technology or recycled scrap. So corresponding technologies need to be also properly parameterized in the sense of showing, consistent production and cost structures, but also, distinguish between different types of materials. So think of metals, non-metallic minerals like cement, plastics, and so on. And in the standard GTAP database, such a presentation is not available. So there is obviously need to introduce this type of details. Of course, this question is not new. So there have been a number of early efforts that have been attempting to incorporate such splits. So, for instance, a number of early studies have relied on their Exia-based multi-region input-output model that provides some level of such details. And I will discuss comparison of the database that we constructed with the Exia-base a bit later in this presentation. In general, Exia-base doesn't always provide enough country details compared to GTAP, especially for developing countries, so which has somewhat limited their applicability of corresponding efforts. And it's not also readily available to be used in their TGE models, which is another potential limitation. There have been a number of studies that use TGE model and GTAP database looking into circularity, but in selected sectors. So, for instance, Winning and colleagues from UCL did a study focusing on steel a while back in 2017. There had been also quite rich work done by colleagues at OECD, so Ruben Pibas from the Link, Lisa Lanzi and colleagues looked into circularity, in particular in plastics, using their GTAP-based TGE model. All these approaches, while introducing valuable inputs, they have some limitations, which we essentially attempt to address in this study. So in case of Exia-base, we found that some of the cost structures and also shares of secondary production do not seem to always match their available country-specific data sources. Focus on specific commodities like steel or plastics also somewhat limits the applicability of these efforts in the more broad economy-wide framework. Not all of these efforts have been also consistently updated over time, so it often has been like a one-off study to assess specific question, which is reasonable in the research community for a specific assessment or study, but of course, to be more widely, broadly used, we would like to have a consistently updated database that is available to researchers. And the last but not least, many of their efforts that I discussed above, they do not provide publicly available data. And so the data is behind the model, but it's not publicly shared, which is essentially their main goal of their GTAP, so providing this data to the community. So what have we done in terms of developing new sectors in the GTAP database to enrich the circularity part? So we have started from the GTAP Power database, which already has 76 sectors and 11 generation technologies, and we have further split selected sectors, expanding the total number of sectors to 99. In particular, we tried to focus both on downstream and upstream sectors. So we started from the mining sector and looked into split it as the extraction sector in GTAP into mining of non-metallic minerals, mining of iron ores, bauxite ores, copper ores, and other ores. Then rubber and plastic sector has been split first into rubber products, and then the plastic has been split into primary plastic production, secondary plastic production, and plastic recycling. Now, the split into primary, secondary, and recycling, as you see, it's typical for a number of sectors. So let me explain a bit better what does it mean and how we have implemented the split. So essentially, the primary sector, be it plastic or steel, uses ore, or in case of steel, or other inputs, non-recycled inputs, so not scrap, to produce their primary commodity. So in case of steel, for instance, this is primarily production using blast furnaces, right? When you use coke and you use iron ore and you produce steel. So secondary sector is activities that relies on scrap or recycled material to produce output. So, for instance, in case of steel, this would be primarily electric arc furnaces production, which uses steel scrap as an input. So usually, these secondary activities more electricity intensive, but less intensive in terms of fossil fuel inputs. And then the recycling activity itself, it essentially is activities that represent the flow of scrap that goes into the secondary production activity. So, and this scrap is collected from multiple sectors. So if you look in the cost structure of secondary activity, it would use inputs from multiple sectors, and then essentially, clean it and recycle it and supply as an input to their secondary production activity, where this scrap is further processed to produce their commodity. And as you can see, this logic of splits has been implemented for plastics, for aluminum, for steel, for copper, and for other metals, non-ferrous metals. In addition, we have also implemented some other selected sectoral splits, which do not refer so much to the circularity, but are rather represent emission-intensive sectors with an aim to provide a better, possibility to use this database to assess some other environmental policies, in particular, European Union's carbon border adjustment measures. So in this regard, we have split cement out of non-metallic minerals, and we have disaggregated chemicals into 3 types of fertilizers: nitrogen, phosphorus, and potassium, and other chemicals. Now, with these sectoral details, we are able to cover essentially all CBAM commodities except hydrogen, which is not much traded. So to implement this split, as you might imagine, we have done quite a bit of data processing and data collection. I won't be going into too much detail on specific data sources, and those data sources are available in their technical notes that accompanies the distribution of the GTAP Circular Economy database. And if you download the package, for instance, from their GTAP website. But just to briefly showcase the steps that we have implemented to develop the database. So, so the first step includes data preparation, in particular construction of their output volumes across different commodities and activities. And in this regard, we have used a number of data sources. For instance, United States Geological Services to come up with mining output values. We have used UNIDO database to complement that, to come up with, for instance, plastics production. We have used Plastics Europe and Veolia databases, and so on. So for fertilizers, we have used International Fertilizer Association data and data from FAO. And essentially with this data, and I'll discuss, there is one more slide that we'll discuss in a bit more detail, specific data assumptions, but this slide is just thank you to provide an overall kind of workflow for developing the database. So with this data that we have collected, we essentially construct the output targets for sectors under disaggregation. And we have also in many cases, to construct the output targets, we had to come up with price estimates. So those are, if possible, derived from domestic prices, if not using some trade-derived prices, so values of exports, imports divided by quantities of exports or imports. We have also, made some assumptions on energy intensities, as I will discuss later, and so cost structures. And then we have combined this data within, their data disaggregation routine, where we use their balancing routine developed by Mark Horridge, so it's a split home utility, and we essentially providing their corresponding cost and supply structures, trade data, tariffs. We develop the database, disaggregating their corresponding flows, and then we further refine their energy and emission flows, in particular for process CO2 emissions using FAO and EDGAR databases. So as I mentioned, we process quite a few data sources to come up with this database, and data availability and reliability also varies by countries and sectors depending on what material we are disaggregating. So just to give you a few kind of key examples of data inputs that we have been using in this database. So for ore mining and production, we have a pretty reliable data from United States Geological Services covering countries and commodities. We also have data on metals production across different technologies. So for instance, for steel, electric arc furnaces to proxy as a secondary production, blast furnaces to proxy as a primary production. So that provides us with a quite reliable data on quantity flows. But then we need to come up with price estimate to convert this to value flows. So in most cases, we derive trade-based prices, but where available, we use domestic price estimates. So if more domestic prices become available, for instance, for steel prices across countries, we might, in the future revisions, revise this assumption. On salmon production, we use data across countries, also sourced from USGS, and price data from the World Bank ICP estimates. So there we have domestic prices. Then for fertilizer split, we follow the approach that was introduced initially by colleagues from Wageningen, Helene Bartlings, and her colleagues. So we source data on fertilizer production from FAO and use a crop emission fertilizer use intensity from International Fertilizer Association. And prices are derived from trade data in the case of fertilizers as well. So finally, in case of plastics and rubber products, the data is pretty scarce. So we relied on Unido to provide some additional initial split shares across plastics and rubber products. But then to come up with the estimates of secondary plastic production, we did quite an extensive literature review. And in cases where possible, for instance, for most European countries, South Asian countries, we managed to find country-specific data of plastic recycling rates. But in a number of countries, we had to rely on regional averages, for instance, for rest of Latin America, for countries which we were not able to locate. So if you have information on country-specific, for instance, plastic recycling rates that we have not managed to locate, this would be a major improvement going forward for revising the database. And finally, for trade data, we use the HS6 level data from the Bachi database developed by colleagues at CP, and essentially we have a mapping between all HS6 codes to the newly disaggregated sectors. So on cost structures and energy inputs, we also relied on a number of data sources. So for cost structures, we use a combination of country-specific input-output tables, which have quite high level of details in selected countries, for instance, in the US, Canada, Korea, Japan. All our tables have at least 100 sectors, and for instance, in case of US, around 500. So we have used some of those sectors to proxy cost structures, and then we combine the data with Exia-based cost structure assumptions. We did some modification for energy inputs. So there we did a data collection from available literature using the so-called techno-economic analysis. So these are essentially technical studies that provide estimates of cost structure, energy flows, fixed costs for specific plants in specific countries. So think of steel production, electric arc furnaces, blast furnaces, or production of, for instance, primary aluminum. So we use those studies and some average of the available studies to come up with assumption of energy use, and first in kilogram of oil equivalent per ton of product, and then converted those to energy use per value of output. So on this slide, you can see some assumptions, for instance, for use of coal, gas, petroleum products, electricity across first steel, primary and secondary, and then other metals such as aluminum, copper, and other non-ferrous metals. Finally, for emissions data, we we use data for both greenhouse gases and air pollutants. So fossil fuel combustion CO2 emission flows are, in case of energy use, combustion energy, fossil fuel combustion, they estimated using their approach that is standard for the main GTAP database, so using IPCC Tier 1 method. And then for the case of process emissions, we source data from the EDGAR database. So for instance, this would be emissions for cement. And then for fertilizers, we calibrate our emissions to the FAO data source. So where available, air pollutants and complementary, so non-combustion greenhouse gas emissions for the new disaggregated sectors are also directly sourced from their EDGAR database. And if EDGAR data provides more kind of aggregate data than we have in the GTAP-C, then the way we also do in the standard GTAP database, we use energy flows or value flows to disaggregate corresponding emissions across more granular sectoral details. As you might imagine, there have been quite a bit of data challenges when we have been developing the database, so I'll just highlight a few of them here. So in some cases, we have been finding inconsistencies between trade data and output data. So for instance, output of steel in country A is reported to be $100 million, while trade data reports that the country exports $200 million worth of steel. So obviously, in those cases, we had to refine the data, making trade and output data compatible. So value of output and intermediate supply in GTAP for the case of the water and sanitation sector, according to IC classifications, should presumably represent the flow of the recycling process itself, right? But when we started comparing the value of output of the this water and sanitation sector with their kind of value of scraps that we would like to disaggregate, in many cases, we have been finding that the output of scrap itself is much, much higher than the output of this sector per se. So it seems that the water and sanitation sector might be providing some only minor margins for processing some scrap, but obviously not representing the value of the scrap itself. So in these databases I have already shown, we have split out their scrap directly from the parent sector. So, and then, the scrap is supplied as an intermediate input from all sectors, but then is kind of split out from the parent sector. So in this way, we managed to overcome, the limitation of their pretty small value flows from their water and sanitation sector. Now, in principle, we might split some small margins from water sector to represent some processing of their of the scrap itself, but obviously not the value of scrap. In a number of cases, not all supply and use structures have been available. So, for instance, in case of recycling or activity, we did not manage to find commodity-specific recycling activity cost structure. So we use some more kind of generic assumptions. Another limitation is that, or challenge, depending how you look at it, would be the fact that we did not manage always to locate the domestic country-specific prices for all commodities, right? So in a number of cases, we had to use trade-based prices, which, might, and then adjusting them with some margins, but, that might not be their most appropriate solution. So in case more domestic prices become available in the future, we might implement some revisions. And finally, in case of selected commodities, for instance, plastics, we did not manage to locate the data for, many countries in terms of the shares of secondary plastic production or plastic recycling. So we had to make some assumptions using regional aggregates, for instance, for the rest of Latin America, assuming the same share across a number of countries. So again, if more data becomes available, that's something we might be able to utilize going forward. So moving to some overview of the constructed database, I'll showcase a few kind of slides with key features. So for instance, here on this slide, you can see the sectoral composition or global average across selected commodities in the GTAP circular economy database. So the blue parts of the bar represent the primary production activity, and orange bars represent secondary production activity or activity using the recycled scrap. And the red rectangular diamonds, they represent the share of the secondary activity. So as you can see, the share of the secondary activity varies quite substantially across commodities. So for instance, it's pretty high in case of steel and aluminum, around 40% globally, and relatively low for plastic, so under 19%. You can also see the values of production. So for instance, iron and steel by far has the most substantial value of output, more than all non-ferrous metals combined. Another feature of the database, as we have distinguished different production processes, is that we have differentiated emission intensities across commodities. And as in most cases, we would see that secondary production activity has a lower emission intensity than primary production activity, which is to be expected. And also that the main differentiation in emission intensities is coming from the scope 1 emissions, so emissions from direct fossil fuel combustion. So for instance, in case of steel, we see that primary, and these are global averages again, as the same as in the previous slide. So we can see that the primary steel production activity has emission intensity around twice, more than 2 times higher than secondary production. This is in the case if we consider all 3 scopes of emissions, right? If we consider only scope 1, the differentiation is much, much higher. So because scope 1 emission in case of secondary steel are relatively low. Scope 2 emissions in case of secondary steel are somewhat higher than in case of primary, because most secondary activities rely more on electricity input. So if we consider, for instance, scope 1 and 2 emissions as, there is considered in a number of CBAM covered commodities, and the differentiation in emission intensities is higher than in the case if we add scope 3 as well. So scope 3 emissions are roughly, similar across both primary and secondary activities. There is some differentiation, but not substantial. So scope 3 are all other emissions apart from direct fossil fuel combustion and electricity related emissions, right? And then we also, trace emission intensities across other commodities. So for instance, cement, fertilizers, we can also see quite a substantial differentiation. For instance, nitrogen fertilizer, which is expected to have much higher scope 1 emissions than, for instance, phosphorus or potassium fertilizer. Now, in many cases, these fertilizers are mixed. So in the application, so, an average fertilizer mix use emission intensity would most likely be an average or some type of weighted average between the 3. So finally, a slide on comparison between Exaiabase and our kind of implementation. And this, just to note that this is comparison for 2014 reference year, so focusing on not on the latest year, but 2014. And so in terms of output, we see that in general we are not that far away, for instance, or although it depends. So for most metals, it's pretty close. In case of plastic, seems as GTAP for 2014 at least has somewhat higher value of output, so it could be also different, different sectoral classifications. But what was a bit more surprising is the difference between shares of secondary versus primary production. So in the case of Exaiabase, we have been observing, and this is this red diamond. So in the case of Exaiabase, as we see, shares of secondary production are consistently lower than in case of GTAP. So for instance, for steel, in 2014, we had around 26% share of production. And in case of Exaiabase, the share is only 6%. In case of aluminum, the depreciation is even more substantial. So could be the case that maybe Exaiabase has not updated shares, at least in the versions that we compare to in their with the more recent data. But their implication of this relatively low shares in Exaiabase is that, for instance, if one would use Exaiabase to simulate increase in secondary production shares to a specific level, then obviously much more substantial effort, for instance, would be needed to increase aluminum share to 50% in case of Exadabase compared to GTAP, and obviously the corresponding cost of the move would be also much higher. So this is one particular implication from this comparison. So in terms of data distribution format, so the GTAP Circular Economy database has been shared publicly around a month ago, and it's shared in all standard GTAP formats. So we have Flex and GTAP, FlexEC and GTAP distributions. We have also for GAMS user GDX containers. The database is constructed for one single year, 2017, which is the latest year of GTAP 11 version. It's nested within GTAP Power database. So if you aggregate all split sectors to the original GTAP sectors, you would exactly get their GTAP Power kind of sectoral classification and value flows. We report emissions of both greenhouse gases and air pollutants, as I mentioned, and it's pretty easy to plug in this database to the GTAP-based CG models. Okay, so now moving to the second part of the presentation, featuring selected applications of the GTAP Circular Economy database. And just to note that these applications have been developed using both previous version of the Circular Economy database, IDEST version 10, and also some using version 11 database. So version 10 has a bit narrow sectoral aggregation, so we did not split there. For instance, fertilizers and cement has been split for only in the later update of the GTAP 10. Still, the Circular Economy database has been used in a number of studies. So starting from this study on circular economy transition in Europe, together with the World Bank colleagues. So that was the first circular economy transition report published by the World Bank. We also did a follow-up study on building greening construction value chains with the International Finance Corporation of the World Bank, and this was the work where we introduced cement split in the database. And finally, another report with the World Bank colleagues focusing specifically on the country-specific circular economy transition in the case of Turkey. Apart from model-based applications, the GTAP Circular Economy database has been also used in a number of more like diagnostic studies, and in particular focusing on the assessment of the carbon border adjustment mechanism measures. So together with colleagues from the World Bank, we have developed this GTAP exposure index, where we try to measure the potential exposure of different countries to the CBAM implementation based on their emission intensities and trade flows from the corresponding country to the European Union. We have also used the GTAP Circular Economy database linked to both GTAP-E and Visage models, CG models, looking into various CBAM assessments for both for EU developing countries, selected countries like Romania, Serbia, Ukraine, and so on. Okay, so now moving to the featuring selected application of the GTAP Circular Economy database. And this application is based on the work that I mentioned we did with the World Bank colleagues for circular economy transition in Europe. We also have a paper based of this work, which is currently under review, and the preprint is available at this link provided here. So as you can see, it's a joint work with the colleagues from World Bank and from Purdue, with Dominique in particular, and Angel. So a bit of a motivation for this work. When we look in terms of emission progress, one might say that Europe has achieved quite a bit of progress over the last decade, and then also at least plans very ambitious measures going forward within net zero targets and Fit for 55 targets. But when we look into material use trends, as I will also show a bit later, progress, especially in selected countries, has not been that substantial. And many papers, they say that this might be partly because there is under research kind of the implications of circular economy transition policies. There has been a review study by Domenech and Van Valkowiak that kind of tried to talked to policymakers and found that many policymakers do not have well understanding of the circular economy policies and concept in general, and what could be the implication of these, in particular, distributional aspects, economic costs, and so on. A number of earlier studies looked into circularity transition for specific countries or selected sectors in the EU, but there has not been really more like a comprehensive study at the EU-wide level. And that's what we try to do in this assessment, focusing on EU in general, but also selected countries, in particular in Eastern Europe, that did not manage to achieve that much progress on circularity in recent years. So these are Poland, Romania, Bulgaria, and Croatia. And with this, we try to estimate both environmental but also socioeconomic implications of the circular economy transition. So on this slide, you can see some circularity material use rates across countries in the European Union, and also 4 countries of our focus. So these are highlighted red. Poland, Croatia, Bulgaria, and Romania. As you can see, all 4 countries have circularity rates below EU average, right? And some of them managed to achieve progress between. So these are changes between 2010 and 2019. For instance, Croatia has improved quite substantially. So did Bulgaria, but then Romania and Poland did not kind of achieve much of a progress over these years. And for instance, in case of Romania, circularity rates have actually declined between these 9 years. So we to assess different circular economy policies, we coupled the developed circular economy database with their dynamic computable general equilibrium model and Visage, the one developed by Dominic. It's a recursive dynamic model. We are running it till 2030, so we wanted to line up with Fit for 55 targets and NDC commitments in the rest of the world. There are some features that are specific to this application. So the model has vintage capital, so both new and old capital with different possibilities of kind of substitution between them. We also use an unemployment closure so that there is, when wages change, there is an unemployment in the short run with a specific parameterization, but then in the long run, we are kind of converging towards their initial unemployment rates. So we did obviously split their different generation technologies in the model. So we have substitution between different renewables, non-renewable generation technologies. And we applied a number of features for when calibrating the baseline, which I won't be discussing in too much detail. So it's discussed in the paper, but for instance, we assume decreasing cost of renewables, increasing preferences towards renewable energy, so some specific commodity and sector-specific energy efficiency improvements, growing electrification rates, and so on. And we used an aggregation of 20 regions and 42 sectors, keeping almost all details of circular economy sectors and different generation technologies. Europe is split into 6 countries/regions. So we have 4 countries of focus, and then the rest of Europe is split into 2 sub-regions. And then the rest of the world we have by 14 aggregate regions and some large economies like US, China, Brazil, India, and so on. And then we developed a pretty comprehensive set of scenarios to look into the circular economy transition policies, where we try to combine both demand-side policies, but also fiscal or supply-side policies. So we started from developing the baseline scenario, which we calibrated to their historical trends combined with projected GDP and population forecasts. For most countries, we implemented first round of NDCs. For Europe, for instance, this is Fit for 40 target, essentially, before their updated NDC. Then we have climate mitigation scenario, which adds mitigation on top of their baseline scenario. And in particular, focusing on EU. So what happens if EU reaches Fit for 55 target, which in our case is essentially carbon price on EU ETS sectors and achieving 55% reduction in 2030 relative to 1990. And the idea here is to look into how climate mitigation policy could impact circularity. And then we do the same with circularity, looking how circular economy policies could impact their mitigation goals. And then we use this essentially baseline plus EU Fit for 55 scenario as our new reference point to assess different circular economy measures. We split the measures, as I mentioned, into demand-side measures, and this include, for instance, consumption bundle shift, where final consumption of materials declines by 20%, but then there is a compensating use of other consumption categories. So think of, for instance, you buy less material goods like cars, but then you might travel more, or you might go more to I don't know, watch movies. So it doesn't necessarily, depending on how this shifts, it doesn't necessarily mean that it is less emission intensive. It would be probably less material intensive. But for instance, if you start traveling more, it could be more emission intensive. So it would depend on your initial kind of consumption patterns. Then we have design change, and the idea here is to try and simulate their impact of changing the design of specific commodity, which might require and would require more services, more R&D. So think of the car which you design with less materials. So for instance, you use glass roof instead of a metal roof, but then you would need to hire an engineer and pay for services to kind of design this more advanced car with less material input. So we have a substitution of inputs between, so we use less material inputs, but we use more services, in particular, engineering services. And similar for lifetime extension, but for final consumption. So that's where, for instance, you use your car longer, but then you need to repair it more. So you spend more on services to repair it. And then another set of policies focuses on fiscal measures, and here we combine taxes and subsidies so taxes on primary materials or mining, and subsidies to secondary production, essentially production from scrap or recycled material. We also considered a couple of other levers. So one is we noticed that there is quite a substantial leakage in this scenario, meaning that while EU reduces their production of materials domestically, it starts importing more material intensive goods, and then material production in the rest of the world increases, and also embodied in imports. So we looked into border adjustment tax, whereas the tax is imposed at the border on the material content of imports, which at the same level as tax imposed domestically. We also looked into different levers of recycling revenue from taxation. So, instead of paying it directly to households, reducing labor taxes. And finally, we have a combined scenario which combines two policies from the demand side and two policies from the fiscal side. So we have preference shift and design change from demand side, and we have extraction tax and essentially production tax from their fiscal side. So just briefly with some key results from this type of scenarios. So first, we find that in the baseline scenario, if we continue, our business as usual, the material consumption and production increases. So this is figure at the upper right corner of the screen. And we also see kind of a growing difference between production-based materials, so essentially how much material is produced in the US within the country, and how much materials are embodied in all consumed goods. So we see that there is a growing difference between production and consumption-based materials, meaning that the leakage kind of continues within EU's kind of business as usual scenario. We also see that in most cases, non-metallic minerals, they kind of dominate their both, especially consumption mix, right? When you look at the consumption levels, although it differs across countries, so meaning that non-metallic minerals, think of cement, and other non-metallic minerals, they are kind of the major contributors in volume, in weight term across countries. So what do climate mitigation policies kind of do to their material trends? We find that climate mitigation policies have quite substantial impact on fossil fuel, both consumption and production, to a large impact production, to a less impact consumption. So there is also leakage here, especially for coal, which declines, anywhere between 25-30 to almost 45% across countries. somewhat lesser impact on gas and oil, petroleum products, so around 15 to 20% depending on the country, and lower for consumption base. So again, energy essentially embodied into imports is not impacted that much due to domestic policies, which is what one would expect. But then relatively minor impact on other materials like metal ores or non-metallic minerals. So there, changes here are between 1% and 2%, which is, not that substantial. And we also see that in very few cases there is absolute decline in material use relative to 2021 levels. So in case of Poland, and also from production-based perspective. And that's because Poland, as if you have noticed in the previous slide, it has pretty substantial share of fossil fuels on the production side, but less substantial on the consumption side, right? So when we reduce coal production, obviously, we have this substantial impact on production-based material use, but not that much on consumption. So, and that's similar, stories observed in other countries. Now, when we looked into all range of scenarios, and this is a kind of pretty packed figure, and I won't be going into much details in each scenario, but I'll just provide a few key takeaways from this. And if you're interested, you can find more details in the paper that I shared earlier. So here we see that there is a complementarity between demand side policies, so those that change, let's say, consumption mix, and those that extend lifetime of commodity use, and production of fiscal side policies. So from their demand side policies, they target both intermediate and final demand, leading to the overall reduction in material use. So they impact both domestically sourced and import goods. But at the same time, they do not change the production mix, right? So you just use less metals or less plastics, but the technologies are not explicitly impacted. On the other hand, fiscal policies, they target the production mix. So for instance, you start producing more secondary or recycled steel, so your recycling rates essentially increase. But at the same time, you do not, there is a leakage, so you do not impact imported materials, right? So you change the domestic production mix, but but there is a leakage, so you start importing more steel embodied in imported goods. So there is this complementarity, and when we combine the two sets of policies, then we are able to achieve quite substantial reduction in material use. So this is this last two columns on this figure. So we are actually able to achieve absolute decoupling, meaning that the material production in absolute terms declines in 2030 relative to 2021 level, but only from the production side. So from the consumption side, these policies are still not sufficient. So we see that some leakage still remains in this case. There is also heterogeneity of impacts across European countries. So we see some variation depending on the initial kind of structure of the material use and production across countries. So for instance, more substantial reductions are observed in Romania, up to 14%, less substantial in Croatia and Bulgaria. So again, depending on the mix of initial material used. And then in terms of impacts on emissions, we see that emissions decline anywhere between 2.5% in Bulgaria, and if you recall, in Bulgaria we have somewhat lower reduction in material use, to over 7-8% in rest of Europe and rest of Eastern Europe, and this is driven largely due to reductions in metal ores, right? These orange bars, as you can see in both cases, and relatively also substantial reduction in some fossil fuel use. So this is kind of positive trade-offs, spillovers from circular economy policies for climate mitigation policies, so reduction in emissions Europe-wide around 6-7%, which can be considered quite substantial.
Maxim, could you wrap up, because there's not much time for Q&A?
Yes.
Yeah?
Sounds good. 3 minutes. Thank you. So finally, on their economic cost side, we find that overall costs in terms of GDP are relatively moderate, so between 0.5% and 1% in the most substantial kind of scenario where we have combined scenario. But at the same time, what we found is that there is this increasing wage skill premium, especially when we shift towards more R&D we stimulate essentially the skilled labor wages, and the wage gap between skilled and unskilled labor wage gap increases, which might require additional policy interventions. So some key takeaways from this policy analysis. We have already discussed them, so I'll skip them to have a more time for discussion. And then just finally to conclude, we have developed this database which splits circular economy sectors, extending the number of sectors from 76 to 99. We also are introduced flows of emissions and their pollutants to the database. So both circular economy and mitigation policies could be analyzed. Database can be easily coupled to their GTAP-based models, and we have done already that in a number of projects. And in terms of future developments, we are currently focusing on incorporating critical mineral supply chains. So this is work with colleagues from WTO and also within the EU Horizon Entice project, where we are also looking into introducing new sectoral splits and technologies into the database. And actually now I'm presenting from the Politecnico di Milano, where we had also a meeting on this to discuss the next steps in terms of introducing new technologies to the GTAP database. And I'll stop here. Thank you. Happy to take any questions.
Thank you. Maxim, there are already a couple of questions in the chat from home. So I don't know if you have access to the chat. You could just read them directly.
Sure. Let me maybe stop sharing, then I can see the chat. Okay. So
one is on the waste. He wants waste coefficients. I don't think you really have that in this database, right?
Right. So I mean, so we do not have, it's not as detailed. We do have value flows of recycled scrap going into, well, we have source of recycling scrap, right? So where it is coming from. And then essentially almost all scrap is supplied to their secondary production activities. So that's the way the database is set up.
So I think that answers the second question as well, which is what is the source of the secondary sector? And it's coming from this scrap and waste sector, right?
Right. So the recycled sector essentially supplies scrap to their secondary production as the input. So think of it, for instance, steel scrap, which is used as an input to the secondary steel production. Yeah.
Then Danita has a question whether we're tracking employment changes, and the answer to that is yes, of course we are, because it's a CGE model. So we do track employment. I don't know, were we using the unemployment closure in this work?
Yeah. For this, for the European circular economy transition, we use unemployment closure. So we also have unemployment results. It's just that I have not presented them here, but we have impacts both on wages and unemployment. Yeah.
And Johan asked whether we're keeping track of material flows over time.
Yes, we do. So we do have complementary material accounts. Now the database that we have shared within the package, it has only value flows, but we are planning to share a complementary kind of information on quantities, right? So essentially all the results that I have presented, they are based on quantities. So this consumption and production-based accounting of quantities. Now, when we come up with values, we use quantity time price, we come up with a targeted value, but then the eventual value in the final database might not be exactly matching the original, target. So, the implied prices when you use the quantities and values, they might not be exactly matching what was initially kind of anticipated, but still quantities are valid to trace the flows over time.
All right, the questions keep pouring in. Let me give the floor to Rafael.
Thanks, Dominique. Thanks, Maxime. Very quickly, 2 questions, and thank you for presenting this. One is on the more like a clarification. I assume you plan to publish also the concordances between the new GTAP sectors and the sort of mapping, right? And the CPC sectors or categories. So do you have this in mind? Because that would be useful if I was thinking, for instance, cement, what's included in there in the new database? Is it from, I assume, the production, but also, I don't know, tiles of cement or precast concrete stuff. So that, yeah, that would be useful for, yeah, if you plan to have that published. And the other one, it's a bit related. It's on more like on the trade part. So you have primary, secondary, and scrap. How do you deal with trade for those sectors that are you have the split? You target the whole sector, or you have specific targets for primary, secondary, and scrap? Yeah. Thank you, Max.
Sure, thanks, Rafa. So on concordances, yes, we are planning to publish it, in particular for mapping to HS6 codes. Now, in case of primary and secondary split, and for instance, so secondary production or scrap production, we just derived it using the recycling rates, right? So, I mean, not all sectors have been derived using IC classification. And for instance, for steel production, we differentiated by technology. So, you have primary technology using blast furnaces, secondary using electric arc furnaces, and in the I6 classification, it would be steel production, right? So there is no explicit kind of split there. So we can describe it in terms of data sources and then have mapping to HS6 codes. But then also, and this relates to your second question on mapping to trade commodities. So for instance, also trade codes do not explicitly consider what technology was used to produce steel. So when we look at trade, we have trade in steel, but then we need to make some assumption what is the share of primary versus secondary steel, for instance, right? In case of scrap, sometimes, well, in a number of cases, we can map it. So we did our best to match that. But then for the case of trade across different types of commodities using different technologies, we just essentially try to proxy it using output shares, right? So, so we have a total trade in steel and then split it across using shares.
Before getting back to the chat, Hide, please go ahead and ask your question.
Yes. Huh? Can you hear me? Yeah. Okay.
Yeah.
Yes. Oh, good.
Yeah. So I think for the cost structure, I mean that slide, and I think I saw like the US, Canada, Japan, Korea. So if I understand correctly, those are basically like the kind of high income countries, and with that kind of like use that for also middle income countries and low income countries. Is that what it is? And if so, you think that's kind of some implications with that? I don't know how important. Maybe it's not that important. I'm not familiar with this topic, I have to admit. So that's, yeah, I was wondering.
Right, thanks. That's a good point. So, I mean, in principle, these are the IO tables that have level of details that, at least in some sectors, matches what we have, right? All other IO tables do not have this level of detail. So for instance, you look into, I don't know, like aluminum, it's not represented in many IO tables. So the cost structures that we come up with, they are a combination of multiple data inputs. So using both techno-economic analysis, for instance, for including developing countries like China or India, IO tables, Exio base, and then we have a constraint of the original cost structure from the GTAP, right? So I mean, they do play a role, but not as substantial because it is constrained by your original cost structure and other data inputs. So when more data becomes available, we'll try to plug it in, which would hopefully improve cost structures, but I wouldn't say I'm that much worried, right? Because we have all these other interacting points. Yeah.
Ruben, if you're online, go ahead and ask your questions.
Yeah. Yes. Hey, hi Maxime. Thanks a lot for presenting this. I'm very happy to see that you added even more commodities than the last time we spoke with cement and fertilizers. Yeah. Very much looking forward to that. One question I had is on the consumption-based indicators. Because we haven't refrained a bit from doing that because we there's a lot of discussions in the literature on differentiated goods, especially between final demands and intermediate demand, where basically the intensities are quite different. And I had a second question that's more related to data, because what you presented on recycling rates were really about values. And I found that there's quite a bit of discrepancy oftentimes in the data between the value terms and the physical terms. So maybe that also explains what you have in Exio-based. So maybe you've thought about that already. Thanks.
Thanks. Yeah. So on first point, what we did, it was a MRO type estimation, trade to final consumption in raw or equivalents. So it's essentially what ends up to final consumers. So pretty conventional approach, right? I mean, in principle, you can also decompose it along the supply chain, but think of the cars that you eventually buy and use, how much commodities are in raw equivalents again. So tracing from mining to point of final consumption. And then second, in terms of comparing in quantities and values, yes, that's a good point. I mean, the comparison we did was in values, right? So it could be the case that if, for instance, different prices would be assumed, potentially this might result in different shares. And we can, that's one option also to compare it to look closer. And also in the comparison more up-to-date version, because that's, as I mentioned, that was for 2014. But at the same time, the comparison was like consistently different, consistently lower in the second case, which was, a bit surprising, at least to me. Yeah.
Thank you. Time is up there. We'll stay an extra 5 minutes, but for those of you who have to leave, allow me to thank Maxim for this great presentation. And we welcome you back to our next webinar, which I suppose will be in the fall. So again, many thanks. Maxim, if you want to handle a few of the additional questions in the chat. There's 2 questions from Xin Yu. If you're online, you're welcome to ask them orally.
Yeah, okay, I'm Xin Yu, and I have 2 questions. The first question about how to interpret the recycling sector's activity. And you have like all sector products as input for recycling sector, but that is not the physical link, right, to the recycling activity. So I'm wondering, do you have like the constraint on the output of the recycling sector? Because in reality, you have like the availability of scrap as a physical constraint for the output level, right? But in the economic model, you can have infinity growth of this sector. So that's the first question. The second question is about what's your assumption about the material intensity for the output, like a different sector? For example, the automobile sector, right? If you make the primary steel more expensive, and if you look at how much steel they use for the automobile sector, do you assume like a fixed material intensity, like each dollar of output, certain ratio of steel there, or you allow some kind of automatic adjustment because they may replace like the steel with the plastic or whatever, right? Then reduce the steel use in the car manufacturing sector. So that's the 2 questions. Thanks.
Okay, great. Thanks for the questions. So both questions, just to differentiate, so there is a database and there is a model, right? So the questions you have asked refer more to the model, right? So it's the way you can treat it, and you can treat it in different ways. So the database represents a snapshot of the economy in the reference year, and then the way you make assumptions how this evolves over time it's on the modeling side, and we have quite a bit of flexibility there. So on the first point of what is the scrap availability, so again the database represents how much scrap is recycled in a specific year. So for instance, in this case 2017, and so all sectors, think of it, you have a production of cars, right? And there is some share of output of that sector that is used as a scrap and is an input to their recycling sector, and same for all other sectors. And then for instance, I don't know, your recycling rate, let's say, is, I don't know, then you need this amount of scrap to produce, 10% of your steel in country A. So that's what represented in the reference here. Now, going forward, obviously, you would need to, depending on how you set up the model, you would need to constrain this. If you think that it is expanding too much, we have obviously, some substitution elasticities. In many cases, for instance, intermediate inputs would be assumed Leontief, right? So for instance, if your car manufacturing sector doubles, then it would provide 2 times more scrap in case you didn't do any additional adjustments to their recycling activity, right? So, but you can adjust it, right? And the second, in terms of substitutability, so there are some substitution possibilities assumed in the model. In most cases, we would keep those Leontief, so using in fixed proportions. But for instance, you have substitution between capital and energy, would be between value added and other intermediate inputs. So you might apply more capital and then use less steel. But for specific sector, you can develop much more elaborate nestings, right? So for instance, you can assume that plastic is substituted with steel, and again, we have that flexibility in the model. So I would say it's up to the modeler to set up these assumptions, right?
Maxim, there's one final question in this chat regarding the XIO base. Amaro wants to know if it's better to use the product by product or the industry by industry version for doing the commodity split.
Right. So it depends where you're doing the commodity the split, right? So to better match. So for instance, if your initial IO table is sector by sector, then you should use industry by industry XIO base. If it is commodity by commodity, then use commodity by commodity. So I would say, to better capture their structure. So here, since we are more focused on sectors, so industries, for instance, secondary versus primary steel production, then we have been using more industry by industry structures.
Okay. And if Home is still online, I would suggest he gets in touch with you directly with his final question. All right. But I think that wraps it up, Maxim. Many, many thanks again. And many thanks for all of those that participated at this webinar. And we look forward to seeing you in the near future. Bye-bye all.
Thank you all. Thanks.